Okay, class, welcome back. This is lecture 3. Today we are talking about graphing linear functions. So we learned about linear functions. Now we're going to learn how to actually graph them. This is something you may have seen before, so it might just be a review for you. That's okay too. Okay, so let's get started. So next we graph linear functions. So what this really means is we draw something, I guess that you could call it like a representation. The graph and the function are connected, and people forget that sometimes, but it's really that we're drawing a representation of all the points that come from using the function. So it's not like I'm just randomly drawing a picture and it has nothing to do with the linear function that you start with. No, the points that I'm drawing through are points that come from the function. So it's best to just see with an example what this means. So remember, we learned linear functions always look like mx plus b. So this one is 2x plus 3. So m is 2 and b is 3. And how do I get points on the graph? We've done that before without actually graphing. All we do is pick an x value and plug it in. So points on the graph come from plugging in x values. That's the basic idea. So for example, if I want to see what 0 becomes when I plug it into the function, which y value I get, all I do is replace x with 0. So I get 2 times 0 plus 3, 0 plus 3, 3. And so that's the y value that I get. So x equals 0 becomes y equals 3. And that tells me, most importantly for now, is 0, 3 is on the graph of this linear function. So we've done something like this before. Let me do one more example. So sort of faster, you can just sort of say y equals instead of f of x and plug it in. Same thing though, 2 times, and I just changed my x to -1 in the function, same function still. This guy up here. Changing my x to -1 now, plus 3 equals -2 plus 3 when you multiply that out. And -2 plus 3 is +1. So another point is -1, 1. So let's just leave it at those two for now. And then let's start drawing the graph. So what we know is that the graph of this function has these 2 points. We don't know all the points, but we could keep getting more and more in the same way. But luckily, 2 turns out to be enough to draw all of them. That's the nice part about linear functions. So let me do it in blue here. So 0, 3 is this guy. So remember how I'm getting that. I'm going to the left and to the right 0 because my x value is 0. And then my y value is 3. So I'm going up because up is positive. So I'm going up 3. And then that's where I'm drawing my point. And I'm labeling it next to it just to be extra clear. So then the other point we got was -1, 1. So that means I have to go left 1 and then up 1. And that takes me to -1, 1. So these are 2 points on the graph. But what about all the other points? Well, it turns out for a linear function, things work out very nicely. For a linear function, the graph, all the other points, all the points, consists of the line, hence the name linear function. So it's just going to be a straight line through any, so I could have picked any 2 points. So what this means is, as soon as I have 2 points, I know the entire graph. The entire graph is the straight line through those 2 points. Of course, you do your best to draw a perfectly straight line. It's very hard without a ruler, but this line should be perfectly straight, not curvy at all, if you've done a good job drawing. And so I have these 2 like bulbous dots here. The rest of the line has all those dots too, but they're just not sticking out. But the point is that the line is going through all the possible points that also work. So if I just draw another point here that's on the line, whatever coordinate it happens to be, if I plug those numbers into the function, it'll work as well. If I plug in that x value, whatever this happens to be, I will get another corresponding y value. So if I've done a very good job, I should get 1, 5. So let's just pretend I drew a perfectly straight line. So I got this green dot and it went right through 1, 5. So I wouldn't have drawn the big dot ahead of time, but it still goes through 1, 5. And in fact, when you plug in 1 to this function, you do get 5. You get 2 plus 3 is 5. So this way I don't have to draw a billion dots everywhere, because I'm not going to just draw a dot every single infinitely many places. It's impossible. Instead, I just draw the whole line. The special property of linear functions is that I can do this if I just pick any 2 points, and draw the line through them, then that'll be the correct line. So I could have gotten 2 points way over here, but I can't draw forever. So it doesn't look like they are being covered, but that's the point of drawing this arrow. It's to say, yes, this just keeps going forever. I just don't have time to draw forever. Same thing over here. Okay. So this is the main thing. All we need to know how to do is draw 2 points, and then we're good. Okay. So let's continue. Let's see, do I want to say this thing yet? Yeah, okay. So now let's just do another little example for practice. So let's graph this linear function. So according to what I just said, we'll learn a faster way in a second, but right now, since this is linear, to accomplish this goal of graphing, I just need to get 2 points. So all I do is get 2 points. That's not so bad, because we have our favorite pal 0, which we love to plug in. It's very easy to plug in. So I would recommend always doing that. The -3 times 0 plus 1, anything times 0 is 0. So you get 1. So here I'm being a little quicker. And I didn't label x and y, but because of so much practice, I know what this means. This means 0, 1 is the point on the graph, because I'm plugging in x equals 0, and I'm getting 1 as the result. Of course, you can use the labels x and y like we have been previously, but this sort of speeds it up quite a bit. Okay, so what about another one? What about if I plug in 1? So this is back to the old notation. I'll say x equals 1, tells you that f of 1 is -3 times 1 plus 1, which gives us -3 plus 1, which gives us -2. So that tells you y equals -2. So this tells us 1, -2 is another point. And luckily, I only ever need 2. So now I can draw my nice graph as best as possible. You are going to need to label the points that you draw because you probably, like me, will not draw perfect graphs. So it will not always be obvious what they are unless you label them. So 0, 1. So that means I go over 0 and up 1 to there. And then 1, negative 2. Oops. So I'll label it. 1, negative 2. I go over 1 to the right, down 2. And then I do my best. That's all any of us can do. Just do your best. Draw a perfectly straight line. And that's it. That's the graph. One thing I want you to notice is how this one is sort of pointing down and the previous one is pointing up. That's always going to happen depending on your slope. So here, m is a negative number. The line is going to go in that direction. So it's -3 in this case. Previously, in the previous example, m was 2. So if m is positive, like 2, it's going to go up. Okay, just some things to notice. And this leads us to something interesting we can actually do with the slope to graph these guys in a different way, which is slightly quicker. And actually just like overall more much better way to do it. So let's do that next. So in fact, we can use m to get from one point to another on the graph. Another very special property of linear functions. The idea being that m is a consistent number. It's always the same number. It's always 2 or always 3 for whichever line you're dealing with. And it's the change in y over the change in x. So if I just change that amount, I can get to another point. That's going to be the idea here. So let's see it in an example. So this one looks a bit weird because you're used to having a number in front of the x, and right now there doesn't seem to be a number there, but there secretly is. It's just one of our favorite numbers. So cool that we don't write it sometimes. So it's just a 1. If you multiply by x a variable by 1, you never write the 1. You just leave it as x. So it's like a secret invisible 1 there. Okay, so that's our slope. So what we're going to do is going to get 1 point. We're going to get 1 point, which we can do very easily by plugging in 0. 0 minus 4 is -4. So 0, -4. So we get 1 point. And instead of getting a second point, we are going to do something a bit cooler. So we're going to think about the slope as a ratio. Really, that's how it was defined. It's really y2 minus y1 over x2 minus x1. So let's think about it instead of as 1. What is this 1 the same as? 1 is the same as 1 divided by 1. So we're going to think about it like that. And then we can go back to thinking about it as a change in y over change in x. So what this is then saying is that we can go from a point that we know to another point on the graph by changing y by 1 and changing x by 1 at the same time. So let's do that. So if I take 0 and I change it by, because it's an x, I change it by 1, I'll get 1 there. And if I take -4 and I change it by 1, I'll end up with -3. So then the point that I get is 1 comma -3. And that point will be on the graph. This is also why sometimes you see M written as the rise over the run. So you could also say it as for every 1 that the graph goes up, it goes over 1. Same idea. You can think of slope in the same way. So if I graph this guy now, or if I want to graph this guy more quickly now, what this is saying is, as soon as I know 0 comma -4, so I go over 0, down 4. As soon as I know this guy, if I want to get to another point on the graph without plugging anything else in, all I have to do is go up 1 and right 1 from there. So I can go up and right, takes me to what I predicted, which was 1 comma -3. And that'll get me a second point. So how can I be sure that this actually works? Well, I could actually plug in 1 and see if I get -3, which I will. If I plug in 1, I will get 1 minus 3, because the function is, sorry, 1 minus 4. Can I ahead myself because the function is x minus 4, which is -3, as we predicted over here. Okay, so this doesn't seem much faster right now than just getting 2 points, but the where it shines is in situations like this next example. So fractions are typically annoying to people, including myself. And so plugging numbers into here sort of gets annoying because you have to deal with fractions and adding fractions. So this is a situation where this newer method is much better. Okay, so here m equals -2/3. We're going to get 1 point like before. Our favorite number is 0. We just plug that bad boy in because anything times 0 is 0. I don't have to deal with fractions so much. That just is a big old 0. Minus 2 is -2. So the point is 0 comma -2. And now to graph the function, I'm going to use this new trick. So I'm going to think of m as -2/3 as being this rise over run thing. So I'm going to think of this as for every 2 I go down, my graph will go to the right 3. The reason it's down this time instead of up is because of this negative here. Last time it was up 1 over 1 to the right 1 because it was both positive, but now we have a negative, so it's down. Okay. So then I'm just going to go down 2 from here and to the right 3. So that will take me to -1, 2, 3, 4, comma 3, which I will, whoops, counted that right way. I did that backwards. Sorry, that was terrible. Close one. Okay, sorry. Over to the right 3 and down 2, 3, -4. I did it backwards. Sorry. Whoops. Okay, so 3, -4 is the next point that I can get, and it's much quicker than having to plug numbers into fractions. And then I finish the graph just by drawing it very nicely. And there you go. One thing you can do is you can also think about this as if you have a negative fraction, you can rewrite it as the negative being on the top or the bottom, because it really means timesing by -1. And you could bring that -1 up top or on the bottom. So you can think about it like this, and then you can think about it as going, for every 2 you go up, you have to go left 3. And that just gives you another way to think about it and get another point in the other direction. So now if I go up 2 and left 3 here, that takes me to what? So I went left 3, so now I'm at -3, and I went up 2 from -2 brings me to 0. So it takes me there. So I can just count it out, or I can take my original point and manually add these numbers. So I could do a -3 and a +2 to get me there, or I could do a +3 and a -2, and that takes me to this one. Okay. That's that example. So next, one thing I want you to notice is that I keep plugging in 0. And that's because it's the easiest number to plug in. But hopefully you've seen the pattern. We always get 0, b. When I plug in 0 to mx plus b, this m times x becomes 0. And so I always get b as my y value. And so this is why you always get 0, b. And this has a fancy name. This is called the y-intercept, because it's where the graph intercepts the y-axis. So the name sort of makes sense there. You can see it, that's what's been happening. The y-axis is the vertical axis, and that is where we keep graphing things. So here too, somewhere, I don't know where I put this one. Yes, there. And it always just so happened to be that number, the b. Okay, just some little things to notice. Okay, and another thing we can do, so lots of stuff we can do. We can also graph linear functions with information instead of the formula, the function formula. So you often see questions like this. Graph the line, so then they might say line instead of linear function, but it's really the same thing, same process. And they'll just say what the slope is directly. And they'll say a point that it goes through or something like this. Going through -2, 4. So again, the new method really shines here because now I don't have a function to plug 0 into. So I can't get my first point that way. So I don't get to do that. And then I can't have a second point by plugging another number in either. So I have to do this new method, but luckily it's nice and quick. So I don't need to know the function at all. I can just sort of follow these directions. So these directions say that -2, so left 2, up 4. So again, this is my x and my y, so I'm going left 2, up 4 to get this point here. And then I can just use my slope to get another point, and I never need the function at all. So m equals 1/2. So that means I'm going to go so if I think about it as rise over run, so I'm going to go up 1 and over to the right 2 from my point to get to another point on the function. So I go up 1 to 5 and to the right 2 to 0 to get me there. So let's label these -2, 4. And then I'm going up 1 more and right 2. So what I'm doing is I'm adding 2 to my x because I'm going right 2, and I'm adding 1 to my y because I'm going up 1 to take me to 0, 5, as I predicted by just drawing. Okay, so then we just draw a line, and that's it. All right, not so bad, I hope. Okay, so we don't even need the function sometimes. Now what we want to do is look at a few interesting types of lines. So parallel lines are the first interesting type. So 2 lines are called parallel if they have the same slope m. So this is pretty quick to see when they're parallel or not. So let's graph these 2 lines and see that they're parallel. So let's graph the line with slope m equals -1/3. That goes through 0, 4. And the line with slope -1/3 also through a different point now, 0, 1. And we'll see that they are parallel and that they never touch. Okay, so first line, maybe I'll do that one in blue. So I go through 0, 4. So I go over 0, up 4. And then I use my -1/3. So I'm gonna go down 1 and right 3. So down 1 and then to the right 3 takes me here. So if I want to label these, this would be 0, 4 and 3, 3. Okay, and then the other one goes through 0, 1 and has the same slope. So I'm still going to go down 1 and right 3 from there. So I'm going to go down to 0 and right to 3. And if I had drawn these perfectly straight, you would see that they never go towards each other. They just follow along the same. And that's because they have the same slope. So you can just have 2 equations given to you instead of 2 pieces of information and also see that when things are parallel. So for example, f of x equals 5x minus 2 and g of x equals 5x plus 10 are parallel lines too. And that's just because I can look at and see that they both have m equals 5. So what will keep happening is they'll both be going over 5, sorry, up 5 over 1 at the same rate. And that's why they'll never touch. Okay, which reminds me, so when there are fractions here, it's sort of easy to see this means up 1, or sorry, down 1, right 3. But what about if it's like a whole number like 5, which is seemingly not a fraction? Well, then to do the same trick, you write 5 as 5 divided by 1. And then you can do the same trick. Okay, maybe you should have brought that up sooner. Okay, so those are parallel lines, and we could draw them very quickly now if I wanted to, because I already know that when I plug in 0, I get b, so 0, -2 is my y-intercept for f of x. And I just have to go up 5. So 1, 2, 3, 4, 5, and over 1 to get to the next point. So this will be 1, 3. And that would be my graph of f of x. So g of x, I did not leave much room for because it goes all the way up, starts up at 10. So we're not going to draw that one, but it would be parallel. Okay, instead, let's think about like the opposite notion of parallel, which is called perpendicular. So the two lines, f of x equals negative 2x plus 4, and g of x equals negative 1/2 x minus 1, are called perpendicular. And we'll see what the property is to be perpendicular in a second, but let's just draw these and see what it means. So what it means is that they meet at a 90-degree angle. So they look like this. If I turn them, they might be sort of like that instead, but there's always going to be this 90-degree angle here if they're perpendicular. And that's what's going to happen with these two graphs. So let's do that and see it. Okay, so let's do it over here, I suppose. So let's graph f of x first. So when I plug in 0, I'm going to get 4. So 0, 4. And that's also because b is 4, and so that's going to be my y-intercept, 0, 4. And then the slope is negative 2. So I think about it as negative 2 over 1, so that I could say that I should be going down 2, right 1. If I think about it as a rise over 1 run, so I go down 2, 1, 2 over 1 takes me there. So this would be 0, 4 and 1, 2. Okay, so to see perpendicular lines, you really have to draw them nice and straight so that they actually cross at a 90-degree angle. So let's do our best. Okay, so this is f of x. So now let's draw g of x. G of x has y-intercept negative at -1, so 0, -1, because when I plug in 0 to this thing, I get 0 minus 1 is -1. And then I can use my slope, m equals, oh, sorry, they should not have both been negative. That the negative 1/2 is supposed to be positive, or this will not work. Change that. Okay. So m is positive 1/2. So this means I'm going to think about it as every time I go up 1, I have to go right 2. So I'm going to go up 1, right 2. From there, takes me to 2, 0. And I think I've drawn it straight enough that you can see that they cross at a 90-degree angle there. If you draw that one, that looks pretty nice. So yeah. So you might be able to see the pattern with just this example, but let's do one more. So when our graph's perpendicular is what we're trying to understand. When does this happen? Well, let's see another example. 2/3 x. So b does not have to be anything. You could just make it be 0. So in this case, let's do that. So these are my two linear functions. So notice that they both have b equals 0. That's just a coincidence. That has nothing to do with being perpendicular, but it's a nice new type of line that we haven't seen before. So let's do it. So these are perpendicular too. So the pattern is that these slopes have to be negatives of each other. So one's got to be negative, one's got to be positive. And the fancy word is reciprocal, but that just means flipped over. So 2/3 and 3/2 are flipped over versions of each other, and one is positive, one is negative, and that's going to tell us that they are perpendicular. So we can graph this one too. So this time, because b is 0 for both of them, that's telling us that the y-intercept for both is 0, 0. So they actually both go through 0, 0. The first one, f of x, I'm going up 2 and right 3, because it's 2/3, to get my next point. And for g of x, I'm going down 3 and over 2 to get my next point. And it looks pretty good again, like a 90-degree angle. So good, great. Okay. Let's see, anything else? So there's lots of possible examples of graphing lines given various kinds of information. So they could say like graph a line that goes through this and is perpendicular to this. And you just use the clues to figure things out that you need. So in the lecture problems, you're gonna have to go through the problems like that. So let me know if you need any help on them. But I think we've gone through enough that you can do them. I will trust you to try. So what we need to do is just fill in the gaps of sort of these like strange extra cases that we never really deal with. So the professor has to walk you through them because they're a bit different. So what about this function? This is a linear function. F of x equals 5. I mentioned it last time, something like this. It has no x's on the right, so what do you do to plug numbers in, and how is this a straight line? Well, let's see what the points are on the graph. So if I plug in 0, my favorite number, well, what happens? What do I do? Well, all the x's become 0. Okay, I changed all the x's to 0. And nothing happened. I just got 5 again. The point of this function is no matter what you plug in, you'll just get 5. Every time you'll get 5. So when I go to graph it, this is saying that the y value is always 5. So 0, 5, 1, 5, negative 1, 5, negative 2, 5 are all on the graph, and they just form a perfectly flat straight line. And that's why another way to see that the slope should be 0, because there is no rise. It's not rising at all. It's just flat. So that's why m is 0 for things like this. So anytime you have a function that equals just a number, it's going to look like this. A straight line at that number. Same thing. Okay, so flat lines like this just come from functions that equal numbers with no x's. And these two are parallel, right? They both have slope m equals 0, which makes sense because they're both flat. So the last kind of weird line is, it's perfectly reasonable to draw a perpendicular line to this line. So a perpendicular line would just be something that goes straight up and down. But then you could say, okay, well, the slope of that line should be, I'm supposed to do, because it's perpendicular, I'm supposed to make it negative. And then I'm supposed to flip 0 over. How do you flip 0 over? Like that? It's really undefined. This is not a number at all. And so instead of that, you just really say that it has no slope, because it just goes straight up and down. And this vertical line is not a function, because it doesn't pass the vertical line test, because it is itself a vertical line. So it's not a function either. But we can write down an equation for it. It's just an equation, x equals a number. because what's going on is all the points on this line just happen at the same x value, x comma blank, the same x value. So for example, I can now quickly draw something like x equals 4. If I want to graph this, it's not a function, but it is something I can still graph because it's an equation. Oops, I sort of missed. Okay, 4 is right there. And it would just be that. And then x equals -3 would be same thing, but at -3. Okay, so that is it for this lecture. I will see you next time.